Welcome back, everybody. In this next video, I want to finish up sigma notation and jump right into the definite integral. All right, for sigma notation, there are some rules that you can follow that can help you solve those problems. The first is called the sum rule. And the sum rule says that if I have k equaling 1 to n of I can split that up into of a k plus of bk. Now you might have thought that you could do this already, but I am confirming that this is legal to do. The difference rule is very similar. AK minus BK equals the sum K equaling 1 to n of AK minus the sum K equaling 1 to n of BK. And again, breaking this up can make things easier. The third rule is called the constant multiple rule. Constant multiple rule says that if I have the sum k equaling 1 to n of some constant times my function, I can basically take that constant, put it on the outside of my summation. Like that. And the constant value rule basically says that if I just have the sum k equaling 1 to n of just a plain old constant, the answer is n, however many numbers there are, the ending number times your constant. All right, so let's do a quick example where we can see some of these rules. All right, so I have a small example here that's k equaling 1 to 3 of k plus 4. Now, I'm going to use the rules because we just talked about them, but you can cycle each number through. An alternate way to do it is to say k equals 1 to 3 of k plus k equals 1 to 3 of 4. Now, I could take the first one and I kind of have to cycle them through, so I have 1 plus 2 plus 3. That takes care of the first summation. And I'm going to add that to, right? Again, I'm going to use rule number 4. So I'm going to say it equals 3 times 4. So 3 times 4, which would be 12. You could also run it through 3 times, say, or 4 plus 4 plus 4, which again would equal 12. So 1 plus 2 plus 3 is 6, plus 12 equals 18. So in this small example, I used 2 of those 4 rules. All right, so remember we're talking about the definite integral. And the definite integral, remember we have a curve, and we're trying to find the area from A to B between the curve and the x-axis. If it's above the x-axis, the area is going to be positive, and if it's below the x-axis, the area is going to be negative, so to indicate that the area is below the x-axis. Now, when we set up symbolically our definite integral, it's going to look something like this. A is our lower bound, B is our upper bound. There's our function. And the dx shows us our variable of integration. So if it's dx, we know that our variable is x. If it's dy, we know our variable is dy. Here's the key with this. All right, so the first rule is that the function must be continuous on the interval. It's not continuous on the interval. There are things we can do, but we can't just do an interval. All right. And the second thing is must be a smooth curve on the interval. Again, if it's not a smooth curve, there are things we can do. We'll actually explore one where it's not a smooth curve on the interval. And I'll just kind of show you the ways to work around these. But in order to just do a very straightforward integral, these two things must be true. All right, so let's do a very straightforward example to start. All right, so I'm going to integrate from -2 to 1. And again, our lower bound is always below. So our lower number is always below. Right? Remember our drawing? A is our smaller number, B is our bigger number. All right? So our smaller numbers, so it's 2x dx. All right? So if we think about it, 2x is continuous everywhere, and it is a smooth curve, which means that we are able to integrate along this interval. So the first thing we're going to do, so the first step is the antiderivative. All right, so the antiderivative of 2x, we raise our exponent 1, divide by the new exponent, 2 divided by 2 gives us 1. So there is our antiderivative. And then I put a line to remember our interval, so it goes from -2 to 1. And now in this section, they actually use the summation notation to finish it off. I'm just going to skip ahead a little bit to the next section, 5.4, and I'm going to use what we call the fundamental theorem of calculus, abbreviated FTC. The fundamental theorem of calculus says that if I take my upper bound and I say 1 squared, and I subtract my lower bound, which would be -2 squared. All right, that would be 1 minus 4, which would equal -3. All right, this is the way we're going to do it for the remainder of the course. So to force you to do summation notation seems a little silly. It's going to take a lot of time. And I'm giving you a little bit of preview of the next section. But I do want to focus on some properties of integration right now. So we're not focused on the fundamental theorem of calculus right now. That'll be the next video. But I do want to focus on a couple of properties that could help you with your integration. Now, the first property says, if I'm integrating and I have the same lower and upper bound, my answer is going to be 0. It doesn't matter what the function is. Function could be anything. Could be trig, could be logs. If my lower and upper bound are 0, and we can illustrate this by making a small graph, right? Here is my function. There's my lower and upper bound. So the area in between those two things, most obviously, is 0. So here is a quick example. I can integrate from pi to pi sine x dx. We know by rule the answer is 0. All right, but let's take a look. What's the antiderivative of sine x? So what has a derivative of sine x? That's negative cosine x. So I'm going to use my fundamental theorem, say negative cosine of pi, right, plus cosine pi. Now, negative cosine pi and positive cosine pi most definitely add up to 0. We don't even need to know what they are because they're going to be the same value, just one's the negative of the other. All right. So the second rule that we have says if I do the integral, now notice my bigger number comes second. What I can do to fix that, because in order to integrate, I need to flip those. My smaller number always has to be on the bottom. So I can take the negative and then I can flip my bounds. All right, and you'll still come out with the right answer. So here's my quick example. So I can, now this is valuable when you see something like this, right? My bigger number's on the bottom. All right, and this is an issue because we can't integrate until our bigger number's on top. So I'm going to do negative 0 to 3 of x plus 2 dx. Now I can integrate, all right? So I have a negative on the outside. I do my antiderivative of x, which would be x squared over 2. Then I do my antiderivative of 2, which would be 2x. And I'm running from 0 to 3. All right? So I'm going to distribute my negative first. So I have negative x squared over 2, and then minus 2x. All right, and again, we're going to shorten this up by, we're going to put in our 3. So if I put in 3, I get negative 9/2 minus 6. Right? There's my upper bound. I'm going to subtract my lower bound. So negative 9/2 minus 6, negative 9/2 minus 12/2, which equals negative 21 over 2. So our final answer, negative 21 over 2. And all that means is, yes, our area is negative, and that's not a problem. It just indicates that the majority of our area is under the x-axis on this interval. All right, so our third rule is called the additive intervals property. And this is going to be one where I'm going to say we have some sort of a problem in our integral. This is when we want to use it. Either we don't have a smooth curve, or we have some problem with continuity. What I can do is I can break up my integral to go from a to c, f of x dx, plus the integral from c to b, f of x dx. All right, so let's take a look at negative 1 to 1, absolute value of x. All right, so now the absolute value of x has a problem, all right? And the problem basically is that in the interval that we're looking at, we do not have a smooth curve. Let's graph this just for a second before we start working. Negative 1, 1, there we go. All right, so what we notice here is we don't have a smooth curve. Now we can't just integrate from negative 1 to 1 because at 0, we have a problem, right? We have this nice corner here which prevents us from integrating. So basically what we need to do to work around this is we need to integrate. Now I'm going to integrate. This function is y equals negative x. This function is y equals x. So I'm going to integrate the negative x function from -1 to 0, and I'm going to add that to the integral from 0 to 1, the function x. So whatever function is between -1 and 0, that's the function you're doing. Then you're doing the other one between 0 and 1. All right. So now the next thing we need to do is our antiderivative. All right, our antiderivative of negative x is negative x squared over 2, and that's -1 to 0. And I'm going to add that to x squared over 2 from 0 to 1. All right, so let's do our first fundamental theorem. So plug in 0, so I get 0 minus -1/2 plus, now I'm plugging in 1, so I get 1/2 minus 0. So then I get 1/2 plus 1/2, which equals 1. And you could confirm this because if I just do a dotted line straight down and a dotted line straight down, I've got two right triangles there, and you can very easily do the area of both right triangles and simply add them up. All right, so the last two properties, all right, are, we have a constant property, so I can go from A to B of k times f of x dx, and that is k times the integral a to b. You could move that constant out so you have less clutter when you're doing your integral. Could just make things easier. And the other property is kind of what we were doing before, which is the integral from a to b. Right? Basically what it's saying is that if I have two functions either added or subtracted, I can say the integral of a to b f of x, either added or subtracted, whatever you have, from a to b of g of x. And we've kind of been doing that one anyway with some of the functions that we've been doing. All right, so I do have a quick example that we can go through. Now this, we don't use the fundamental theorem of calculus because again, that's the next section. So here's the way the example would look, right? I have evaluate the integral from 1 to 3 of negative x squared plus 4x minus 3 dx using, now I'm going to give you some information. The integral from 1 to 3 of x squared dx equals 26 over 3. And this would be given right in the directions. The integral from 1 to 3 of x dx equals 4. And the integral from 1 to 3 of just plain old dx equals 2. All right. So what this example is doing is trying to say, let's use some of those properties that we just discussed in order to get down to be able to use some of the information in the directions. All right. So I can do, I'm going to change. All right. So I'm going to change my color. So I'm going to say it's the integral from 1 to 3 of negative x squared dx plus the integral from 1 to 3 of 4x dx minus the integral from 1 to 3 of 3 dx. So I use my sum and difference rule, my rule right up here, where I can take each individual function and I can make separate integrals out of them. All right, now I have a constant in the first two that I want to take out. So I can say negative integral 1 to 3 of x squared dx plus, I can take out the 4, the integral from 1 to 3 of x dx Now I can take out the 3, so I have minus 3, the integral from 1 to 3 of just plain old dx. Now, do I need to do the integrals? Well, if I didn't have the extra information in the directions, right here, the answer would be yes. I would have to do the integrals and use my first fundamental theorem of calculus. Again, the first fundamental theorem of calculus is in your next video. So we're going to use the information in our directions to make a substitution. All right? So I have the integral from 1 to 3 of x squared dx. I'm simply going to say I have negative, and I'm going to substitute in 26 over 3. Then I'm going to add that to 4 times, right? I can take that, and I'm going to substitute in 4. And then I'm going to take minus 3. And I'm going to substitute in at the end 2, right? And again, I got those directly from the information contained in the problem. All right, so why don't you at this point evaluate that? You should be able to do it without a calculator. And I'll talk about the answer on the back end. All right, so I got 4/3 as my answer. That's what you should have got. All right, if you didn't get 4/3, go back and check. Guys, I want to thank you for listening. This was a slightly shorter one. We went right from our summation notation, the last couple rules, right into the basics of the definite integral. And follow up next time, 5.4, with the fundamental theorem of calculus. And this is really when the definite integral will hit our stride. Thanks for listening, and I'll see you all next time.